Okay, so moving right along through chapter 15, on to 15.4, a uniformly charged disk. So we're going to use the equations for a charged disk quite a bit in this class. In terms of circuitry and other concepts, turns out to be a really powerful object. So we're going to really look in detail of where this equation has come from. Okay, so we have our disk. There it is. And so the first thing is to recognize what we could view a disk as. So in this case, we don't want to do a series of point charges. How do you even do that? That's just infinite point charges. So what we'd want to do instead is we could think of a disk as being a series of infinitely small charged rings. And in this case, each one of these rings, we've got the radius of the disk, and then each ring would have its own radius, little r, that would vary as we summed up all the pieces. And this is a much more doable way of approaching it, where you just have, we know what happens as the rings get bigger and bigger. How do you even model a point charge system like that in a reasonable and easy way? I mean, there are ways to do it. It's just far beyond this class. Okay, so now that we've decided the shape that we're going to be doing, let's write it out. So a disk is several charged rings and each ring varies by radius r. Little r. So we've got the ring of radius big R and the little rings which vary by radius little r. Okay, so step 2. We want to look at the contribution of the electric field of each piece. And this is also where we set up those easy coordinate systems. Okay, so we're going to set the center as the origin. Oh, this is running out of ink. Let's see if this works any better. Okay. So then we know that as we go outward, we can see here the radius little r is going to change. So the summation variable is little r. Okay, so we need to think about where we're going to be observing. So when we've got the rings, we know that the center of a ring is 0. So once again, we're looking at observing on Z. So as you get further and further and further away on axis. Okay, so R in this case, if our observation location is in Z and the center relative is just the origin, then our R vectors is going to be 0, 0, and Z. And that means that the magnitude of R is equal to Z. And R hat is equal to R over R magnitude, which is 0, 0, 1. Exactly like you would expect. Okay, so now we need to set up our delta E equation. And for this, we're just going to use the contribution of one ring. We know how to calculate a ring. Beauty of deriving different shapes, then we can use them. So it's 1 over 4 pi epsilon naught delta Q times Z over R squared plus Z squared to the 3/2 times 0, 0, and 1. That R hat we calculated. So this is the expression for a ring. Okay, so now we need to look at delta Q as a fraction of the total charge. Now this is going to be a little bit different because if we look at the size of the different rings, we can see they're not all the same size. So we need to have a different way of approaching this. Okay, so delta Q is equal to the total charge times the area of a ring divided by the area of the disk. Okay, so in Q is of course total charge. Okay, so let's have an expression to go for this area of the ring and the area of a total disk. We know how to do that. So you can imagine that a ring is basically just a rectangle rolled out flat. So if I take this paper that I'm writing notes on, you can see I can easily get a very thin disk or a very thin ring. I roll it out, then we just have a little rectangle, and this will have length 2 pi little r, and this is delta r. So this is a ring rolled out. Sounds like an art house film title. Okay, so now that we have the expression for the area of a ring, we can just plug that into our equation. And so delta Q is equal to the total charge Q times 2 pi r delta r, so length times width, divided by pi r squared, which is the area of a circle. Okay, so now we have our expression delta E, we've got our expression for delta Q. We can start putting the pieces together. So delta E is equal to 1 over 4 pi epsilon naught capital Q times 2 pi r delta r over pi big R squared times Z divided by r squared plus Z squared to the power of 3/2 times 0, 0, 1. Okay, so in this we can see that both this delta Q and R are going to be different for each piece. So we need, but in both cases they do depend on that variable R. So the R is driving a little bit more than the previous shapes that we've been looking at. So let's think about the components. All right, so we know that this is a series of rings, and we know that the X and Y components cancel each other out in rings, so really Z is going to be the only non-zero component. Okay, so let's think about EZ. And remember, you'd want to justify that, so using the ring, Z is the only non-zero. And once again, I've picked up the pen that is running out of ink. Okay, so delta EZ is equal to 1 over 2 epsilon naught Q over pi r squared times Z over r squared plus Z squared to the power of 3/2 times r delta r. Okay, and then to get this ready for integration, we're going to convert it into dE. So dEZ is equal to 1 over 2 pi epsilon naught Q over pi r squared times Z over r squared plus Z squared to the power of 3/2 r dr. All right, so general, you would of course stop here. Classical, we're going to keep going. So step 3, we want to sum it all together. All right, so EZ is going to be equal to the integral from 0 to r. So we start at the center of that circle at 0, and we go all the way out to r. 1 over 2 epsilon naught Q over pi r squared times Z over r squared plus Z squared to the power of 3/2 r dr. And so EZ is equal to 1 over 2 pi epsilon naught Q pi r squared Z 0 to r little r over r squared plus Z squared to the power of 3/2 dr. And then this is an integral I want you to do on your own to practice use substitution. So you're going to use U is equal to R squared plus Z squared. So do unknown. All right, so after you solve this using U substitution, you get that E sub Z is equal to 1 over 2 epsilon naught Q over pi R squared 1 minus Z over R squared plus Z squared to the power of 1/2. And we can make this a little bit more simplified. So we know that the area of a circle is equal to pi R squared. So we can chunk that in right there. And we see that E sub Z is equal to Q over A divided by 2 epsilon naught 1 minus Z over R squared plus Z squared to the power of 1/2. And then step 4, we want to just double check it. Conceptually, it makes sense. We only have a contribution in Z. The units work out. So let's look at some special cases. Because whenever we can make something easier, we should do it. So let's look at very close to the disk. So 0 is much. In this case, our electric field becomes approximately Q over A divided by 2 epsilon naught 1 minus Z over R. And then we should look at if Z over R is very small, then 1 minus Z over R reduces to 1. And so you get the electric field is approximately Q over A divided by 2 epsilon naught, which is something that we will see several times in this class.